This is lab 5, where I've chosen to observe the motion of a falling slinky. To be specific, the objective of this lab is to observe the motion of an extended slinky when it is dropped from rest and the bottom part of the slinky is hanging in the air. So the question is, does the bottom part of the slinky stay stationary when the top of it is released, or does it move along with the top of the slinky and hit the ground first? Then we'll discuss what forces explain this observed motion of the slinky, and this lab in particular observes the motion of the bottom part of the slinky. That is, the bottom part of the slinky is what is modeled in GlowScript. So now let's watch the video. So in the video, you can see that the bottom part of the slinky stayed at rest till the top part hit it, and then the slinky in its entirety reached the ground compressed. So to analyze the motion, I used Tracker. I used the bottom part of the slinky as the origin right here. But however, since this wasn't my video, it was difficult to find the length of the slinky as it could vary from slinky to slinky. But it turns out someone else on the internet had the exact same question and instead used the height of the host, which they got from Twitter. So after putting this height in, I marked the position of the bottom part of the slinky over 500 frames. Using Tracker, I was able to get the Y value positions of the slinky over time. Now, to model this motion computationally, we need to understand what forces are acting on the bottom part of the slinky. So we observed that when the slinky is dropped, the top part of the slinky moves to meet the bottom part, and then they both fall together. In the first part of the motion, which is the top part falling while the bottom part stays at rest, there are two forces acting on the bottom part of the slinky, the gravitational force and the tension force of the slinky. These are equal to each other, which is why it stays at rest. In the second part of the motion, the entire slinky falls to the ground, and there is the gravitational force acting on it and the drag force acting on the bottom part of the slinky. These are the physics formulas I used. So first is Newton's second law with its position update formula and velocity update formula, and also the formula for gravitational force, which is mass times the gravitational constant. This is equal in magnitude to the force of tension observed in the first part of the motion. And third, we have the drag force in the second part of the motion, which is the proportionality constant times the square of the magnitude of the velocity. After setting the initial conditions of the experiment in the code, this part of the code shows the first part of the motion, which is when the bottom part of the slinky is at rest. The gravitational force is equal to the force of tension, and thus the slinky stays at rest, and the position of the slinky is a straight line. The second part of the motion includes gravitational force and drag force, which I've described right here. And then we get the updated position using the formulas for Newton's second law, which I already described earlier. I then used all the plot information from Tracker for the experiment and GlowScript for the model and charted it into this line graph. The small differences can be attributed to marking errors in Tracker because the video was pretty blurry. But overall, you can see that the experiment and the model have very similar motion trajectories. So this graph comparison concludes Lab 5.